Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine for a second, you're driving down this long, flat stretch of highway. You know the kind, where you can just see for miles, totally clear day. You're cruising along, and you pass a police car parked on the shoulder. The officer points a radar gun at you, clocks your speed.
I think most of us have felt that specific spike of adrenaline.
Absolutely. But then a mile down the road, there's another police officer, also an expert, also holding a state-of-the-art, perfectly calibrated radar gun, and he clocks you too.
Okay.
Now, imagine both of these officers are the best in the business. Their equipment is flawless. They technically never make mistakes. But a week later, you get the ticket. The first officer says you were going 73 miles per hour.
Right.
The second officer says you were going 67 miles per hour.
That is a very confusing court date.
Right. Who do you believe? They're both experts. They're using top-tier technology to measure the exact same event, your car moving. But the numbers don't match.
In our world, you'd probably, blame it on a faulty battery or something.
Exactly. But in astrophysics, this isn't about a speeding ticket. It's about the speed of the universe itself. And this discrepancy, it is, and this is not an exaggeration, the single biggest headache in modern cosmology.
You were referring to the Hubble tension.
Yeah.
And you're right to frame it as a headache. It's really more of a crisis. We aren't talking about a car. We're talking about the fabric of space expanding.
The universe getting bigger.
And we have two very different, very precise ways of measuring that expansion. And for the last decade, they have just refused to agree.
It's the cosmic speed trap. And usually when we talk about this, the solutions people propose are, they're incredibly wild.
Oh, yeah. You get into some really high concept stuff.
People start talking about dark energy changing over time or gravity leaking into other dimensions. But today, we're looking at a new contender. A new paper just dropped, literally today, February 15th, 2026, that suggests the answer isn't some new phantom force. It might be something surprisingly domestic.
Domestic is an interesting word for it, considering the scale. But yes, the fundamental force is certainly something you encounter in your kitchen every day.
We were talking about magnetism. The same force that holds your grocery list to the fridge might just be the key to fixing the biggest broken number in physics.
Although, to be fair, the magnets we're discussing today are a little different than a fridge magnet. We're talking about primordial magnetic fields.
Primordial, so ancient.
Incredibly ancient. These are weak, invisible fields that were generated mere milliseconds after the Big Bang, and we think stretch across the entire cosmos.
So on today's deep dive, we are going to look at why the universe's speedometer seems broken. We're going to unpack this new paper by researchers Pogosian, Jadamczyk, and Abel. We'll find out what a picogauss is.
And why clumping is the technical term you need to know.
And how these invisible magnetic webs might be the bridge between two numbers that just won't play nice.
And I think this is the most exciting part. We're going to explore how this research doesn't just fix a math problem. It potentially opens a window into high-energy physics that we could never, ever hope to replicate in a lab on Earth.
Using the universe as its own particle collider.
Precisely.
Okay, let's unpack this. We have to start with the problem itself, the Hubble tension. I feel like we hear this term a lot, but let's really drill down. It all starts with Edwin Hubble, doesn't it?
It does. You have to go back to the 1920s. Before Hubble, the scientific consensus was that the universe was static. It was just there. Eternal, unchanging.
The way it is now is the way it's always been.
Exactly. But Hubble pointed his telescope at the night sky and just fundamentally shattered that view of reality. He showed that the universe is actually getting bigger. Galaxies are moving away from us.
And it wasn't just random movement, right? There was a distinct pattern to it.
A very clear pattern. He found that the farther away a galaxy is, the faster it's receding from us. It's the classic analogy of dots on a balloon.
Right, as you inflate it.
As you inflate the balloon, every dot moves away from every other dot. But the dots that start further apart seem to move away from each other much faster because there's just more balloon expanding between them.
And that rate of recession, that specific relationship between speed and distance, that's the Hubble constant.
Correct. It's the fundamental expansion rate of the cosmos. Now, the units we use to measure it are a bit of a mouthful. Kilometers per second per megaparsec.
Okay, hold on. Let's break that down. Kilometers per second, that's easy. That's just speed. But Per megaparsec. What on earth is a megaparsec?
Right, let's build up to it. So a parsec is a unit of distance we use in astronomy. 1 parsec is about 3.26 light years.
Which is already an incomprehensibly huge distance.
Massive. But a megaparsec is 1 million parsecs.
So we are talking about a distance of roughly 3.26 million light years.
That's the one. So when we say the Hubble constant is, for example, 70 kilometers MPC, it means that for every megaparsec you go further out into space.
A galaxy appears to be moving away from us 70 kilometers per second faster.
Precisely. It's a rate of stretching. If a galaxy is 1 megaparsec away, it's moving at 70 kilometers. If it's 2 away, it's 140 kilometers. It just scales up.
Okay, got it. So we have the speed limit we're trying to measure. Now, so as we said in the intro, there are 2 police officers, 2 ways to measure this number. And this is where the fight starts. Let's call them Method A and Method B. Method A is the direct approach, the look-out-the-window method.
That's a good way to put it. Method A looks at the late universe, the universe as it exists now, or in the relatively recent cosmic past. This is the method that follows directly in Edwin Hubble's footsteps. We look at galaxies and we measure how fast they're moving away.
Okay, speed seems easy enough to measure, right? You just use redshift.
Speed is very straightforward, yeah.
Yeah.
We look at the light spectrum. If it's shifted toward the red, it's moving away. We can measure that to an incredibly high precision. The tricky part, the absolute nightmare of observational astronomy, is knowing exactly how far away the object is.
Right.
You can't just, use a tape measure.
Because in space, you completely lose depth perception. A really bright thing far away can look exactly the same as a dim thing that's close up.
Exactly. To solve this, astronomers use something called standard candles.
I love this analogy. Break it down for us.
Okay, so imagine you are standing in a long, dark field at night. You see a light in the distance. Is it a dim little flashlight 10 feet away? Or is it a massive searchlight 10 miles away? You can't really tell just by looking.
Right.
But what if you knew for a fact that the light was a specific brand of 60-watt light bulb?
Then you'd know exactly how bright it should be at the source.
Exactly. If you know its intrinsic brightness, the wattage, you can measure how dim it appears to your eye, and then some simple physics tells you exactly how far away it must be to look that dim.
So we need to find the universe's 60-watt light bulbs.
And we have them. Our primary standard candles are what we call type ES supernovae.
Exploding stars. But why are they all the same brightness? Explosions seem like they'd be messy and, kind of random.
They are incredibly messy, but the physics that triggers them is remarkably consistent. A type AS supernova happens in a binary star system. You have a white dwarf, which is a dead super-dense star core orbiting a companion star.
Okay.
The white dwarf's gravity is so strong it starts to steal matter from its companion. It just siphons it off, getting heavier and heavier. But there is a strict fundamental limit to how heavy a white dwarf can get.
The Chandrasekhar limit.
That's the one. It's about 1.4 times the mass of our sun. Once the white dwarf hits that exact limit, it can no longer support its own weight against gravity. It collapses and detonates in a thermonuclear explosion.
And because the mass at the moment of detonation is always the same.
The brightness of the explosion is always the same. It's nature's standard bomb.
Wow.
We also use another kind of star, Cepheid variables, which pulse. And the speed of their pulse is directly related to their intrinsic brightness. So by combining these measurements, using the Hubble Space Telescope and now the James Webb Astronomers, have built this very precise cosmic distance ladder.
They climb that ladder, they check the speedometer, and what number do they get?
Consistently, when looking at the late universe with supernovae and Cepheids, we get a Hubble constant of roughly 73 kilometers per second per megaparsec.
Okay, 73. Lock that number in. That's officer number 1.
Right.
Now let's look at method B, the indirect approach. This is the look at the baby pictures method.
Yes. This method is completely different. It has nothing to do with stars or galaxies. It looks at the cosmic microwave background, the CMB.
The afterglow of the Big Bang itself.
The oldest light in the universe. It was released when the cosmos was only about 380,000 years old. Before that moment, the universe was this hot, dense, opaque fog.
Like a plasma.
Exactly. And when it cooled enough, that fog cleared and light could finally travel freely. That light has been streaming through space for 13.8 billion years, stretching as the universe expands, until today it falls into the microwave part of the spectrum.
So we have this picture, this snapshot of the baby universe, and when we look at it, it's not perfectly smooth, is it?
No, not at all. It has tiny fluctuations, hot spots and cold spots that correspond to tiny, tiny ripples in density.
So we have a map of the infant cosmos. How on earth do you get a speed limit out of a static map?
Well, we use our best understanding of physics. It's called the Standard Model of Cosmology. It's this incredible mathematical framework for gravity, matter, dark energy, everything.
Right.
We take the data from that baby picture, which was measured with incredible precision by the Planck Space Telescope, and we plug it into the model. We basically hit fast forward on a giant cosmic simulation.
You're simulating the entire 13.8 billion year history of the universe?
In a sense, yes.
Yeah.
We say, okay, if the universe started with these specific ingredients and these specific density patterns, and if the laws of physics are what we think they are, how fast should the universe be expanding today?
So it's a prediction. It's like looking at a toddler's growth chart and predicting how tall they'll be when they turn 20.
It's a very, very precise prediction based on what we believe to be fundamental physics.
Mm-hmm.
And when we do that calculation, the number we get is not 73.
What is it?
It is roughly 67 kilometers per second per megaparsec.
67 versus 73. Now, I have to play devil's advocate here for a second. To someone on the street, that sounds pretty close. If I guessed a jar had 67 jelly beans and it turned out to have 73, I'd be thrilled with myself. Are we sure this matters?
In many, many fields, that would be a celebratory agreement.
Mm.
But in precision cosmology, it is a disaster.
You're a disaster.
Yes, because over the last decade, both sides have refined their measurements again and again. The error bars, the margins of uncertainty, have shrunk to be incredibly small, and they do not overlap anymore.
So it's definitely not just a rounding error.
The statistical significance is over what we call 5 sigma. In science, that means the odds of this being a random fluke are less than 1 in 3.5 million. It is a genuine, undeniable conflict.
So either the police officer looking at the supernovae is wrong, maybe our understanding of cosmic dust is off, or our light bulbs aren't as standard as we think?
Or the officer looking at the baby picture is wrong.
Or the law of the road itself is wrong. The physics we're using to connect to the two is broken.
Exactly. If the measurements are as good as we think they are, then our standard model, our entire understanding of how the universe evolved, is missing a piece. We need a tiebreaker, or a whole new rule of physics.
And this brings us to the new research. This paper, published today, authored by Pogosian, Jadamzik, and Abel, they are suggesting the missing piece is magnetism.
Yes, primordial magnetic fields. And to understand why this is such a compelling idea, we actually have to talk about another mystery, a totally different problem in astrophysics that seems unrelated but might just be the key to the whole thing.
I love a good subplot. What's the second mystery?
It's the mystery of where cosmic magnetic fields come from in the first place.
I feel like we take magnetism for granted. Earth has a magnetic field. It protects us from solar radiation. The sun has one. We have magnets on our fridge. It just seems like it's everywhere.
It is everywhere. And we understand planetary and stellar fields pretty well. They're generated by dynamos, basically churning, conducting fluids inside the planet or star. The spinning molten iron in Earth's core is what creates our field.
It's like a generator.
A natural generator, yes. But when we look out at the cosmos on a grander scale, we see something puzzling. We see massive magnetic fields threading through entire galaxies.
You mean the Milky Way itself is magnetic?
Very much so.
Mm.
And not just galaxies. We see magnetic fields in the gas between galaxies and clusters. And we think they might even exist in the great cosmic voids, the emptiest parts of space. The question is, where did those come from?
Right, it's the classic chicken and egg problem, isn't it? Did the galaxy form first and then spin up a magnetic field? Or was a magnetic field there first, maybe helping the galaxy to form?
And here's the problem with the galaxy first idea. It is very, very difficult to explain the strength of the galactic fields we see today just by spinning them up from nothing. You need a seed. You need some tiny initial bit of magnetism to get the dynamo process started.
A starter yeast for the sourdough, if you will.
That's a perfect analogy. Without a seed field, the math just doesn't work to grow the strong fields we observe. And this is what leads to the theory of primordial magnetic fields. The idea is that magnetism wasn't made by stars and galaxies. It arose in the chaos of the Big Bang itself.
So the universe was born with magnetism woven right into the fabric of space-time.
That's the theory. It could have been generated during cosmic inflation or during one of the big phase transitions in the first fraction of a second. But for a long time, this was just a hypothesis to solve that one problem, the seed problem.
But now, these authors, Pogosian, Jadamzik, and Abel, are asking a much bigger question. They're asking, if these primordial fields exist, could they do more than just seed galaxies? Could they actually fix the Hubble tension?
Exactly. They wondered if this one invisible force could solve two of the biggest problems in cosmology at the same time, the seed problem and the broken speedometer problem.
Okay, so let's get into the mechanics of this. How does a magnetic field, primordial or not, actually change the expansion rate of the universe? It feels like those two things shouldn't be related at all.
To understand the mechanism, we have to go back to that moment I mentioned earlier, the formation of the cosmic microwave background. It's an era of the universe called recombination.
Right, let's set the scene. The universe is about 300,000 years old. It's hot, it's dense, it's a soup.
It's a plasma. And that means it's just too hot for atoms to hold together. The electrons, which have a negative charge, have been ripped away from the protons, which have a positive charge. They're just flying around independently.
And because those electrons are free, they scatter light like crazy.
Like a thick, impenetrable fog. A photon, a particle of light, can't travel more than a tiny distance before it smacks into a free electron and gets bounced in a random direction. The universe is opaque.
But all this time, the universe is expanding and it's cooling down.
Right. And eventually it gets cool enough, down to about 3,000 Kelvin, that the protons can finally capture the electrons. They can finally bond. They form the first neutral hydrogen atoms.
They hold hands.
And this is the crucial part. Neutral hydrogen does not scatter light the same way. The fog lifts. The universe, in an instant, goes from opaque to transparent. That moment is called recombination.
Okay, so that's the standard story. Now, let's throw a primordial magnetic field into that hot, foggy soup. What changes?
Well, magnetic fields interact with charged particles. They push and pull on them. It's called the Lorentz force. So now, imagine you have this plasma. Gravity is trying to pull the matter together into little clumps. But the intense pressure of all that radiation is trying to push it apart. It's a constant tug of war.
And the magnetic field jumps in as a third player.
Yes. And what it does is it creates what we call baryon clumping. The magnetic fields create these localized spots of pressure and tension in the plasma. They force the charged particles, the protons and electrons, to clump together just a little bit more than gravity would do on its own.
So the soup gets lumpy, a little bit lumpier than it would have been.
The soup gets lumpy. And here is the key bit of chemistry. Recombination, the process of protons and electrons forming those hydrogen atoms, happens faster in denser regions.
Why is that?
Think of it like a crowded party or a singles mixer. If you have 100 people spread out across a huge football field, it might take a long time for people to find each other and pair up.
Right, they're too far apart.
But if you crowd all 100 people into one corner of the room, they're constantly bumping into each other. They're going to pair up much, much faster.
That is a surprisingly perfect analogy. So by clumping the matter together, the magnetic fields make it easier for protons to find their electron dance partners.
Exactly. And the consequence of that is that recombination as a whole finishes sooner.
Sooner. That's the key word, isn't it? The fog lifts earlier than our standard model assumes it does.
The universe becomes transparent earlier. The baby picture is taken earlier in cosmic history.
Okay, I'm following the physics, I think, but I'm still missing the final connection to the 67 versus 73 number. Why does the fog lifting a bit early change the speed reading we get today?
This is the most technical part, but it's also the most elegant. Remember method B? The indirect method, the one using the baby picture?
The one that gives us 67, yes.
It relies on measuring the size of the patterns in the CMB. Those patterns, those hot and cold spots, are essentially sound waves that were traveling through the plasma.
Sound waves in the early universe. That's just wild to think about.
We call them baryon acoustic oscillations. Imagine dropping a stone in a pond. Ripples spread out. In the early universe, these ripples of pressure traveled through the plasma until the moment of recombination. As soon as the universe became transparent, the plasma turned into neutral gas, and the sound waves basically froze in place.
So the size of those frozen ripples we see in the CMB is determined by how long they had to travel before everything froze.
Exactly. The distance they were able to travel is called the sound horizon. And for decades, it has been our standard ruler for the early universe. We know, or at least we thought we knew, exactly how long that ruler is.
But if the magnetic fields made recombination happen sooner,
then the sound waves didn't have as much time to travel.
the ripples are smaller.
The ruler is shorter.
Oh, wow. Okay, let me just restate this to make sure I've got it straight. We have been looking at these patterns in the sky, these ripples, assuming they were made with a ruler that is, say, 12 inches long.
Right.
But because of the magnetic field speeding everything up, the ruler was actually only, say, 11 inches long.
That's a perfect way to describe it.
And if you measure a giant room with a ruler that you think is the full length, but it's actually too short, you're going to get the dimensions of the room wrong.
You will miscalculate the distance to the CMB. and as a result, you will miscalculate the expansion rate required to get from there to here. If you correct for the magnetic fields, if you shrink the ruler in your calculations to its true shorter size, then the inferred Hubble constant has to shift.
It goes up.
It goes up. It moves from 67 toward 73.
Boom! The magnetic bridge.
Magnetic bridge. By accounting for these fields, the baby picture prediction can be brought into alignment with the supernova measurement. The two police officers are actually agreeing. We just interpreted the second officer's data wrong because we didn't know about the magnetic interference on the road.
That is just incredibly elegant. It doesn't require inventing some new, weird kind of dark energy. It's just saying, hey, everyone, we forgot to account for the magnetism.
It is elegant, but elegance doesn't automatically mean it's true. For that, you need proof, or at the very least, you need rigorous simulation. And that is what this new paper finally provides.
Right, because up until now, this was mostly a back-at-the-napkin idea, wasn't it? Or at least a simplified one-dimensional calculation.
Correct. Back in 2020, two of the authors, Karsten Jadamczyk and Levon Pogosian, first demonstrated this effect was possible with a simplified model. But real plasma physics is messy. It's turbulent. You can't just approximate three-dimensional chaos on a piece of paper.
So what did they do differently this time?
They ran the first full three-dimensional magnetohydrodynamic MHD simulations of the primordial plasma with magnetic fields embedded in it.
They built a virtual baby universe in a supercomputer.
A virtual slice of one, yes. They tracked the history of hydrogen formation in 3D. They didn't just guess at the clumping effect. They simulated the fluid dynamics, the magnetic stresses, the photon interactions, everything.
And what did the computer say?
The results were compelling. They compared their simulation data against the actual observations from the Planck satellite and other cosmological data sets, and they found that the real-world data shows a consistent mild preference for the existence of these magnetic fields.
Mild preference. That sounds a little cautious.
Scientists are professionally cautious. It's in our DNA. We rely on sigma values to quantify this stuff. In statistical terms, the preference they found ranges from about 1.5 to 3 standard deviations, or sigma.
Okay, translate that for us. What does that mean?
Well, 5 sigma is the gold standard for a discovery. That's when you pop the champagne and start booking your flight to Stockholm for the Nobel Prize.
Right.
3 sigma is generally considered strong evidence. So 1.5 to 3 is a meaningful hint. It's like finding a clear fingerprint at the crime scene. It doesn't prove who did it yet. Maybe there's another explanation for the fingerprint, but it matches your main suspect. It tells you that you are definitely on the right track.
So it's not a done deal, but it's a very, very strong lead.
Exactly. But there's a second piece of evidence in the paper that, in my opinion, makes it even stronger. It's the specific strength of the magnetic fields required.
This is the pico-Gauss thing we mentioned in the intro.
It is. The simulation tells us not just if there were fields, but how strong they would need to be to solve the Hubble tension. The number the data seems to favor is between 5 and 10 pico-Gauss.
Okay, let's contextualize that. A pico-Gauss. I had a magnet on my fridge. How many Gauss is that?
A typical fridge magnet is about 50 to 100 Gauss. The Earth's magnetic field, the one that moves your compass needle, is about half a Gauss.
And this is a pico-Gauss.
Pico-Gauss is 1/trillionth of a Gauss.
So these are, they're unbelievably weak fields.
Vanishingly weak. You would never, ever feel them. But remember, they are pervasive. They span the entire cosmos. So the total energy involved across that scale is actually significant. But here's the real aha moment.
I'm ready.
Remember the seed problem, the other great mystery of where galactic magnetic fields came from.
Yes, the sourdough starter for galaxies.
Right. Well, astrophysicists have calculated independently, in a totally separate line of research, completely unrelated to the Hubble tension, how strong a seed field would need to be in the early universe to eventually grow, through dynamo effects, into the galactic fields we see today.
And let me guess.
The required strength they calculated is roughly 5 to 10 pico-Gauss.
No way.
Yes way.
It's the same number.
The Goldilocks strength needed to fix the Hubble tension is the exact same strength needed to explain why galaxies are magnetic in the first place.
That feels like more than a coincidence. That feels like a major puzzle piece just clicking perfectly into place.
It fits both locks with a single key. That is what makes this paper so exciting to the community. Nature tends to be efficient. It seems highly unlikely that the universe would have one field to solve the Hubble tension and a totally different, unrelated field to seed galaxies when one field can do both jobs perfectly.
So if this turns out to be true, it really does rewrite the history of the early universe.
It absolutely does. It means that magnetism was a fundamental player from the very, very beginning. We usually think of gravity as the main sculptor of the universe, but this suggests magnetism was holding the chisel too.
And that leads to some pretty profound implications. You mentioned at the start that this could be a window into physics we can't do on Earth.
Well, think about where these fields would have to come from. We said primordial. That means they were generated in the first fraction of a second after the Big Bang.
During the era of inflation, or maybe the electroweak phase transition.
Precisely. These are moments when the universe was incredibly hot and dense.
Yeah.
Energy levels that are billions or even trillions of times higher than anything we can generate in the Large Hadron Collider.
We just can't build a machine that big or that powerful.
No. But the universe was that machine. And if we can confirm these magnetic fields exist, and if we can measure their properties precisely, their strength, their shape, they act as fossils from that era. They are like a diary entry from the moment of creation.
That is just mind-blowing. We're analyzing a glitch in a cosmic speedometer to try and read a diary from the first picosecond of the Big Bang.
That is the beauty and the madness of cosmology. Everything is connected. You pull on one tiny thread here, a small discrepancy in expansion rates, and you find yourself unraveling the fundamental physics of the first second of time.
So what's the next step? How do we go from a meaningful hint to a confirmed discovery? How do we get from 3 sigma to that 5 sigma gold standard?
We need better maps. The paper notes that this theory survives the most detailed test available today. But available today is the key phrase there.
We need better eyes on the sky.
We need to look at the cosmic microwave background with even higher precision. And specifically, we need to look for very particular patterns in the polarization of that ancient light.
Polarization is the direction the light waves are sort of wiggling.
Correct. And magnetic fields should leave a specific twisting signature, a kind of fingerprint on the polarization of the CMB. If the fields are there, they should have twisted the light in a very predictable way that we could look for.
Are there missions planned to do that?
There are. There's the Simons Observatory being built right now in the Atacama Desert in Chile. There's a satellite mission from Japan called Lightbird, and the huge CMB S4 project. These are all upcoming experiments designed specifically to map the CMB polarization with unprecedented sensitivity.
And if they see that specific twist?
If they see that signature, then the Hubble tension is likely resolved. We can say with confidence the universe is expanding at 73 kilometers MPC, and the reason we thought otherwise is because we forgot to include the magnetism in our baby pictures.
And the standard model of cosmology.
It survives, but it gets an important update. It's not broken, it was just incomplete. We add primordial magnetism to the official recipe book of the universe.
It's amazing how science works like that. We hate it when the numbers don't add up. It's frustrating. But that frustration, that tension, is actually where the discovery lives.
Precisely. If the numbers had matched perfectly 10 years ago, if both methods gave us a clean 7/8, we never would have looked this hard for these magnetic fields. We might have missed this entire layer of reality. The tension is what forced the innovation.
The grit in the oyster makes the pearl.
A poetic way to put it, but yes, completely accurate.
So to recap our journey today, we started with a broken speedometer. 2 trusted methods giving us different answers for the expansion of the universe. A 67 versus a 73.
We introduced a suspect.
Yeah.
These weak, invisible, ancient primordial magnetic fields.
We then looked at the mechanism. These fields made the plasma in the early universe a little bit clumpy, which caused neutral hydrogen to form sooner than we thought.
Which, in turn, shrinks the sound horizon, our cosmic ruler. And when we use the correct shorter ruler, our measurement of the expansion rate shifts up, moving from 67 to match the 73 from the local observations.
And finally, we saw that the new 3D simulations back this all up, showing that the specific strength of magnetism needed to fix the tension, those 5 to 10 picogauss, is the exact same strength needed to solve a totally different problem. Why galaxies are magnetic at all?
A single unifying solution to 2 major cosmic puzzles.
It really makes you think about the invisible scaffolding of the universe, doesn't it? We look up at the stars and we think, that's it. That's the universe. But there are these vast, invisible webs of force magnetism, gravity, dark matter that are really running the show.
We are just seeing the foam on top of the ocean. The deep currents underneath are what dictate where all that foam goes. This paper suggests that magnetism is one of those deep, powerful currents that has been pushing and pulling on the cosmos since the very beginning.
It's a powerful reminder that the universe is a connected system. You can't tweak the beginning without fundamentally changing the end.
And you can't fully understand the end without knowing exactly what happened at the beginning.
I want to leave our listeners with a final thought then. We've been talking about magnetic fields today, something we usually associate with, fridge magnets and compasses. But if these fields really did shape the early universe, if they really did alter the timeline of creation, what other invisible forces might be out there pushing and pulling on the cosmos that we haven't even thought to put into our equations yet?
That is the ultimate question, isn't it? If we could miss something as fundamental as magnetism for this long, what else are we missing? Is our standard model incomplete in other ways? Are there other fossils from the Big Bang hiding in plain sight in the data, just waiting for someone to ask the right question?
Something to wonder about next time you look up at the night sky. Or, I suppose, next time you look at your refrigerator.
Indeed.
Thanks for joining us on this deep dive into the magnetic universe. Keep looking up and keep wondering.